Okay, so we just learned how to use the power iteration method, and actually more specifically the inverse power iteration method to find the smallest eigenvalue eigenfunction, which is the ground state wave function and the corresponding energy level. And this is easy enough to write the code for, but this is not exactly the form of the operator matrix that we're using. This is a full matrix here, even though we're only using the three diagonals in the center. And so if we did this computation for like a 1,000 by 1,000 point matrix, that would be a huge amount of memory and wasted computation time dealing with all these zeros. So in the previous video, we made each of these diagonals its own vector. And so we're going to need to write our own solve linear equations algorithm to deal with that special case, because this will only work for a full matrix. And the way that you do this, the way you solve this linear equations, is using something called Gauss-Jordan elimination, followed by a process called back substitution. So let me explain what this means. So here's a set of linear equations that you might encounter in an algebra class or something, and you have three unknowns and three equations, and you could solve one of the equations for an unknown, substitute it into the next equation, solve that for another unknown, substitute it in the next equation, and eliminate all your variables and solve each one by one. You can express the same set of linear equations as a matrix equation. So you have this operator matrix A times x equals b. You can see b is just the numbers here to the right of the equal sign, and a times vector x would be -2 times x0, which is up here, plus -1 times x1, plus 7 times x2, and so on. So you can see how this matrix equation equals this set of equations. And the way that you need to organize your matrix in order to solve the equations is you need to get it into upper triangular form, which is like this, where you only have numbers on the diagonal and above, and everything below the diagonal is 0. Why is this the desired form? Well, because then if you write it back in the form of a set of linear equations, your bottom row is an equation that only has one unknown. Your next to bottom row has two unknowns, but one of them is the unknown you could solve for in the bottom equation. And so therefore you could solve for x2 here, substitute it into this equation to solve for x1, substitute x1 into this equation to solve for x2. That should actually be an x2. That's a typo, sorry. So this is the algorithm you can use to do that. I won't go over it in detail here, but it's basically just divide the proper elements of b here by the correct index of a to obtain x, and so on, everything that I just described. And you can just follow a set procedure to do that. But that doesn't answer the question, how do you get your set of equations into this upper triangular form? So you have to do some factoring and a process called Gauss-Jordan elimination. And it says that you can add any row here in your matrix equation to any other row, which you can see how that works if you write it in its normal equation form. And also you can multiply any row by any number, which would work because you could multiply, for instance, both sides of this equation by 2 and it wouldn't change the resulting answer. And by doing different iterations of just those operations, you can cancel out these subdiagonal numbers and make them 0. Okay, so you can go through one at a time, make a new element 0. Won't go through that in detail, but you can look through this on your own if you want to really understand where this algorithm is coming from. But this algorithm has 3 nested loops in it. So the operations scale with the size of the array cubed. So it's not very efficient, and for large matrices, it takes a very long time. But we can write a special version of that called the Thomas algorithm for tridiagonal matrices, because you can see there's only one diagonal below. There's only this subdiagonal here below the main diagonal. These are the only numbers we need to factor out with Gauss-Jordan elimination. So we can do one pass of Gauss-Jordan elimination. And that algorithm will scale with the size to the first power. So this is the entire Thomas algorithm here. Here is your Gauss-Jordan elimination. You just go through and you're factoring these out, which is the E vector. And then you do your back substitution once you have your upper triangular matrix to solve for all the unknowns. Okay, so here's what that equation or that program looks like right here. So just put all of that code in a formula node to make it easy. We have our 3 diagonals of our operator matrix. We have B, which is our guess at a wave function that is being iterated on every time. There's this shift value, which is what's going to allow us to actually get not just the lowest energy solution to Schrödinger's equation, but we can shift any of the solutions to be the closest to 0, so we can solve for any of them. And here's our resulting matrix, our array here in our AX equals B equation. Here's X that we're solving for. So I've typed in some test numbers here, as I have in the PDF. So for E, we've got 0, 4, 3, -9. For F, we've got -2, 5, 6, 4. For G, we've got -1, 2, 5, 0. And for B, we have 1, 7, 0, 3. And if I run this, do I get the right numbers? Yes, I do. So if you want to understand how this algorithm works, I would recommend plugging in some numbers for very small arrays and working through them one by one. But this is how you can solve a set of linear equations when you have a tridiagonal matrix.